in the case where the initial velocity, see if we can get that up just a little higher. Not seeing the arrow over the V0, but that's okay. Okay, the initial velocity is at angle alpha, otherwise identical to the preceding situation. Now, if we're given delta x, delta y, and alpha, we want to find V0. So what we're given is how far the projectile goes before it lands, the height from which it's projected, the angle at which it's projected, and again, we're wanting to find V0. Now, this is very similar to the analysis you need to do in order to analyze what happens when the ball rolls off the incline and falls to the floor. If the incline is horizontal, then this would apply. If the incline is not horizontal, then you have a vertical component to the initial velocity, and the equations change. So, your R of t function is, as always, V0 ti plus x naught, and I've put the x naught in here this time, and negative 1/2 gt squared plus V0 yt, and that should actually be y naught, but we know that in this case y naught is delta y, so I've just kind of jumped the gun and substituted that. And that gives us this R of t function. Okay, the R of t function is V0 cosine alpha t, and back up to that, what's the x component of the initial velocity? So should be clear, that it shouldn't need any explanation, that the x component of this vector is V0 times the cosine of alpha and that the y component of the initial velocity is V0 times the sine of alpha. Okay, so we have this vector function. Now, again, it's possible to put this in two columns. You have the x motion here, the y motion here, and they are independent except that they share the time interval. Trying to develop a functional approach in terms of vector functions. Okay, we want to see the development of a vector function. It's very important later on, especially in physics. This is completely equivalent to what you would do if you set it in an x column and a y column and reasoned it out that way, but we're going to treat it this way. Okay, so what we have is we have the R of t vector. The V0 x is V0 cosine alpha multiplied by t, and that's times your I vector. And the V0 y is V0 sine alpha. The y naught, which is what I really should have written here, is delta y though, so we have delta y here, and right there's our R of t function. How do we, what's the condition here? Okay, the condition is I've said here we want to solve this, and that's actually not right. I said that over here, I said we're given delta x, delta y, alpha, and V0. But in any case, our condition is that when the y component is 0, the x component is delta x times I, with all the rest of the parameters. So we're still going to set all this equal to this. And that's going to give us an equation actually is going to give us a pair of equations. When we set this vector function equal to this vector function, we find that V0 cosine alpha t is going to equal our delta x, and that this negative 1/2 gt squared, etc., is going to equal 0. We have one equation for the I components, one equation for the j components, and that gives us two equations, and it's a good thing because there are two things we don't know. Okay, what don't we know here? And we don't know the time when the thing strikes, and we don't know the angle alpha at which it starts. So I'm going to have to flip the boards. We'll continue in a second. Okay, so our situation for the draw a small picture here just to indicate we got V0 here, we got angle alpha here, And we got the projectile going up and coming back down out here somewhere. So that's a very small picture, and you can't even see it because, I'll just move the camera back a little bit. Okay. Not sure how much sense that makes, but that's the situation. Okay. So we're given delta x, delta y, and alpha, and our conditions come down to this. The projectile lands, so it's at y equals 0 when the x displacement is delta x, and this leads, and you can flip back to the previous, flip back 30 seconds or a minute, and you see where this all comes from. So we reduce the problem to the fact that v naught cosine alpha t times delta x, which is your initial x velocity, that's v naught cosine t, times the time, has to equal your x displacement to the point where the thing strikes the ground. And the other equation is the equation for the uniformly accelerated motion, the motion accelerated in this direction. Since v naught has an angle alpha, of course alpha could be positive or it could be negative. I've drawn it positive. There's nothing in that picture that prevents alpha from taking a negative value. These equations are going to apply either way. In any case, the initial y velocity is v naught sine alpha t. The y acceleration is g, so we get the negative 1/2 gt squared from integration. If you want to memorize the formula, okay, but if you get asked to integrate it, you're going to need to do that. And delta y. So all that adds up to 0. And we can solve these two equations for now I'm forgetting what the initial conditions were, and I just washed that board. I thought alpha was unknown and v naught was known, but it could be that alpha, it doesn't matter. The analysis is the same either way. The alpha is known, and we're trying to find v naught, which would be the case for the projectile off the ramp. Okay, so if it's alpha that's unknown, you can solve for alpha and t. If it happens to be v naught that's unknown, then you need alpha, and you'd be able to solve for v naught and t. So here it says find v naught and t. And that would make sense in terms of the situation. I kind of lost track of just what we were trying to find here. Again, these equations work either way. If it's alpha and t, you can solve the equations for alpha and t. If it's v naught and t, you can solve for v naught and t. And I'm not going to go through the solution of that equation. You should do that. And of course, if you have questions, I'll be glad to address them.